Today's lecture is going to look at how the system balances cardiac output and its vascular function. We've mentioned before in a few lectures the concept of cardiac output. We said that this was the heart rate times the stroke volume. In times where we need an increase in cardiac output, our sympathetic nervous system can kick in and provide an extra squeeze. Beta-adrenergic stimulation can manipulate the calcium signaling, leading to a stronger contraction and a higher stroke volume. We have two other mechanisms to change cardiac output through physical changes. One way to increase the cardiac output is by stretching the chamber to accommodate a higher starting volume to eject. The stretching of the actin and myosin's overlap invokes the principle outlined by the Starling curve. Here we can plot the end diastolic volume of the heart, which is the preload, against the cardiac output. We see that as we increase the delivery of blood to the heart, there is an increase in cardiac output. Retaining fluid in an attempt to increase cardiac output is a dangerous game, and it is one of the tough aspects of heart failure. Your body needs the excess volume to maintain a cardiac output to compensate for a failing myocardium, but the excess volume causes pathologic changes within the body and can have a myriad of effects on the liver, lungs, or vasculature. Another way to increase cardiac output is to increase the size of the cardiac myocytes. This is known as hypertrophy. This is usually in response to a pressure-based stressor, like hypertension or aortic stenosis. The heart essentially just gets stronger to overcome a barrier, and the thicker muscle can raise the stroke volume. We think of this on the Starling curve as an increase in contractility. If we were to have a pure increase in contractility given the same preload, the cardiac output increases while the end diastolic volume stays the same. We are going to add another curve on top of this one just to make things a little more complicated. Let's take a look back at the curve that had the increased preload. If you notice, we stayed on the same Starling line. This is because our body matches venous return to cardiac output. This has to be the case because if input didn't match the output, then blood would pool in one place or the other. This venous return graph plots the cardiac output to the right atrial pressure, preload, or the end diastolic volume. I'm going to draw it out on top of the Starling curve because that's where you're most likely to encounter it on a test. Let's take a patient who's just suffered a cardiac arrest, is in VFib, and has a cardiac output of 0. There is still blood present in the left ventricle, and we're going to assign it an arbitrary value. If we immediately defibrillate this patient and they have a return of spontaneous circulation, there will be an increase in the cardiac output. This patient's cardiac output increases as it draws from the venous system's reservoir with each heartbeat. This shifts the balance of fluid from the venous system over to the arterial side. This increases the blood pressure. However, over time, this decreases the venous reservoir that we can pull from, which drops the preload. If you look back at the Starling curve, a drop in the preload sends the curve to the left. This is how the two forces find a happy medium. They try and find a place where the system is in balance between the venous return and the stretch principle. So if we look back at that original curve that had the increase in preload, we'd see that the purple curve, which is the normal venous return, shifts to the right. This gives us the new venous return curve outlined in green, which brings us to the new cardiac output. These are tough topics, but you need to become comfortable interpreting these graphs. My suggestion is to learn how to change each variable and what that looks like on the graph, and then apply different pathological conditions to each change in physiology. Thank you again for watching, and good luck with your studies.